Hi, and welcome to video note 6.3, where we're going to talk about subsets and extrapolation. So one of the context we're going to be looking at here is about homes in Sunnyvale and how much they cost. And so one of the contributing factors to the price of a home is its size. And the most common way to measure size for a home is square footage. So here's a sample of 49 homes for sale in Sunnyvale, and we're going to compare the listing price that are on Zillow there and the size listed on Zillow as well. And this is size in square feet, listing prices in millions of dollars. So you can see the scatter plot there, and the green line on your paper, it doesn't look green, but if you wanted to, you could pull out a different color and go over it in green so that way you can sort of see it. The equation is given there, and the R squared value for this is 0.174. I want you to take a moment and comment on how well do you think our regression model is doing here? How well does it fit the data? How accurately would it predict for us? Take a moment, pause, and come on back. All right, so hopefully you said something similar to what I'm saying here, which is that our model is not really doing a great job of representing our data. It is the least squares regression line, so it is the line of best fit, but we can see that it doesn't really represent our data very well at all. Any prediction that we make here is likely to have either a very large positive residual, meaning we're under predicting by a lot, or a very large negative residual, meaning we're over predicting by a lot here. There are very few cases where we're going to have a small residual here. And that's a problem, okay? Means that our data, our model is not going to be a good predictor for us here at all. Now, what's going on? Well, you might notice that there is sort of some clusters in our data here, okay? There seem to be some points up top and some points down below. There's actually three clusters here, three what we call subsets. Subsets are groups within a larger pool of data that are different in a specific way, and thus often should be considered separately when considering regression lines and linear models, okay? So the subsets here are three, actually. There are three different subsets. We have houses, okay? The things that are listed on Zillow as being houses. We have manufactured homes. Those are often in considered like trailer parks, but they are already pre-manufactured homes that they just sort of set in place in a spot. And then there are your townhomes and condos. Those are typically sharing walls and ceilings and floors and things like that, unlike houses which are freestanding. So if we were to separate those subsets and come up with the individual linear models for each of them, here's what we would have here. I'm not going to say them all out, but you can take a look at it and see just how different they would be compared to just lumping all of the data together. So take a moment and respond to this question here, which is, how do the linear models separated sort of compare to the one when everything was clustered all together? You should go ahead and write about that, and we'll talk about this in class, as well as talk about some other examples of subsets. All right, on to the backside here. So now we're going to consider the linear model below that shows the average age at marriage from men between the years 1890 and 1940. You can see that we only have data for every 10 years there. What we're seeing here is a strong negative linear association between men's age at marriage and the number of years since 1890, okay? And it might even be considered an outlier at 1940. This one right here, you might consider it an outlier, but if you are like, no, that seems fine to me, I totally understand as well. But it's the linear equation that we have here is given there in bold, and the R squared is 92.64%, doing a bang up job there at explaining the variability between our variables there. What we're going to do here is we're going to use our linear model to make a prediction. We'd like to know what is the average age of marriage predicted for men in 2017. Why don't you go ahead, pause the video, and find that, and then come back and see what work I did. So here is my work. Okay, I plugged in 127 because that's the number of years since 1890. If you plugged in 2017 as your input value there, then you obviously are going to get a very different number. Go back and fix that for us. So what we got was a prediction of 21.22 years, okay? Just a skosh over 21 years old. Before I tell you what the actual age was, why don't you take a moment to think about, do you believe that number? Do you think that that is lower or higher than what you would expect? So, as it turns out, the actual average age at marriage for men in 2017 was 29.5 years, okay? Much higher than what we expected there. So, let's talk about this. What happened? Why did our model give us a prediction so far off? Well, what we just did there is something called an extrapolation. We were asked to extrapolate. An extrapolation is when we use a linear model to predict values beyond, outside of those found within the domain of our data, okay? Our age data only went up to 1940, which means we were trying to predict 77 years into the future. That's a lot into the future that we're trying to predict there. So the idea behind extrapolating, it's nice, right? Because oftentimes we are trying to predict things outside our data set to sort of see what's going on, especially things that have to do with time. We would like to know weather in the future, stock markets in the future. But extrapolating can be highly unreliable, as it assumes that all other conditions are still holding true, okay? And so this is actually why a lot of our intercepts, when we interpret them, are complete nonsense, because usually our explanatory variable at 0 is not part of our data sets. That's talking about newborn babies. That's talking about when there's a shoe size of 0, things of those weird natures that just don't make sense. So in our particular case, with the men's marriage age case, okay, there's been a ton of things that have changed since that first set of data. We were looking at only the late 1800s to early to mid 1900s. Lots have changed. In fact, there's more data. Here at the scatter plot, we can see that there's now more data there. We still have the old data dating all the way back to 1890, but we have a ton of new data from 1950 and onward here. So I want you to brainstorm this, okay? So the whole idea why extrapolating is dangerous is because the conditions don't hold true. Things aren't the same as they were in the set of data. So for us, what changed over time here, okay? Couple things to note. There's a sudden dip in age right after 1940. Why do you think that's the case? Can you put it in historical context? And then you can see that after 1960, there's a climb in age where men are getting married later in life. Why is that the case? I want you to jot down your ideas in this space here, and we'll talk about this when we get into class. If you're ready to move on, let's move on. So, in summary, it's generally best only to interpolate, okay? So that is to predict values within the domain of our data. Or if you are going to extrapolate, only a little bit, okay? So don't take data from the late 1800s and try to extrapolate to the early 2000s, but you could probably use that data to maybe make some predictions about the early 1900s. Our data went all the way to 1940. We probably could have talked about 1950 and not been too far off. You can actually see that in our scatter plot down here, that in 1950, our model would predict here, not too bad, not too bad. That residual is not too bad at all. But to make a prediction way beyond that was just an absolute bad move on our part, okay? I'm going to finish out this video here by giving you a multiple choice question test tip for you. Sometimes you might have been tossed a problem where it seems like it's just a prediction problem. Well, they're like, here's your regression equation. Great. What are we going to get if we, plug in x equals 17 or whatever? you should pay attention to what they're actually asking you to predict. If it is, in fact, interpolating, okay? If it's within your data set, go for it. It's totally fine. Do the work, plug and chug, come up with your answer. But if you notice that, oh, x equals 17, that's way outside my data range. I don't have any x values that are 17 and nowhere even close to that. All my data is from 40 to 100. You're extrapolating, and you should look for the answer choice that says something like, not enough information. Because it's true. If you're going to extrapolate, you're going outside of the information that you have. So you would need to know more information. You need to know more data roughly around the value you're trying to predict for in order to actually be able to do this. So don't plug and chug. Think critically about these things. Sometimes it is literally just plug and chug and you circle, yeah, I got 23 as my y value, great. But sometimes it's a trick and you don't want to fall into that trap, okay? So remember to do your explanations here up above about why we're seeing the trends in our scatter plots in these different regions. And then don't forget to also do the last little bit here about how these linear models compare separately when instead of all grouped together. We will see you in class.